The Angstrom Exponent. Every time light passes through smoke, it loses something. Some of it gets absorbed, some of it scatters away. What's left on the other side tells you the smoke was there, but it doesn't tell you what the smoke was made of. That's where the Angstrom exponent comes in. Here's the simple version. Smoke particles interact with light differently depending on their size. Small particles are picky. They block blue light far more than they block yellow-green light. Big particles aren't picky. They block every color about the same amount. If you shine light through smoke and measure two different colors, the difference between them tells you something the color alone never could: how big the particles are. The relationship follows a simple power law. Optical depth at a given wavelength equals a scaling constant times the wavelength raised to the negative alpha power. That alpha is the Angstrom component. A high alpha, somewhere around 0.5 to 4, means extinction drops off fast as wavelength increases. That's the signature of small particles dominated by scattering that depends heavily on color. A low alpha, closer to 0, or 1, means extinction barely changes with wavelength. That's the signature of large particles, where light just gets blocked the same way across the spectrum, regardless of color. Here's the problem with single wavelength instrumentation. Extinction depends on two things. You can't separate how many particles there are and how big each one is. One equation, two unknowns, you're stuck. Add a second wavelength, and that changes. The ratio between the two measurements cancels out particle count and leaves you with something different, almost entirely by size. That ratio is the Angstrom exponent. Why it matters for smoke. For combustion smoke specifically, this distinction has practical meaning. Black carbon from flaming combustion tends to sit at a lower alpha, closer to 1. Fresh smoldering smoke, richer in small organic particles, tends to run higher, 2 or above. This means a two-channel optical depth ratio can start to distinguish flaming from smoldering combustion by not looking at flame directly, but by looking at what the smoke itself is made of. A single brightness reading tells you smoke is present. Two wavelengths compared correctly start to tell you what kind of smoke it is. That's the Angstrom component, not a measurement of how much smoke there is, but what it's made of.